Hello everyone, and welcome to the Section 3 examples for the Mathematical Proofs lecture series. So we have 7 problems that we are going to look at and prove using the trivial, the vacuous, and the direct proofs. So let's take a look at the first problem that we have here. So we have let x be an integer, and we need to prove that if 54x is divisible by 3, then 216x is divisible by 3. Well, let's first start this problem off by doing some scratch work. So let's see if 3 is divisible by 216. So yes, it is. So 3 times 72 equals 216. So we can prove this trivially. So with that, we can write our proof. So let's put our title, and then we will first define our variables. Let x be an integer. So then 216x equals 3 times 72x. So therefore 3 divides 216x, and the statement is true trivially. And we have just proven this statement. So it's a pretty easy and straightforward one, because we proved that the second statement, 216x is divisible by 3, is true. And therefore, if you remember the truth table, that means that the implication is true. All right, so let's go to problem 2. So we have let n be a natural number, and we need to prove that if 5n plus 4 is less than 4n plus 2, then n squared plus 5n minus 6 is less than n to the fourth plus n squared minus 1. Well, let's take a look at the first statement. The statement that's the implier. So let's let 5n plus 4 be less than 4n plus 2, where n is a natural number. So then if we subtract 4n, we're left with n plus 4 is less than 2. Then that implies that n is less than negative 2. However, n is a natural number, so this is false for all n. Therefore, the statement is true vacuously. So because we looked at the first statement, 5n plus 4 is less than 4n plus 2, and showed that it's false for all values of n, then we vacuously proved that this implication is true. All right, let's move on to problem 3. So we have let a, b, m, and n be integers where m and n are greater than or equal to 2, and n divides m. So we need to prove that if a is logically equivalent to b mod m, then n divides a minus b. All right, so this should be a pretty straightforward direct proof. So let's define our variables. Let a, b, m, n be integers, where m and n are greater than or equal to 2, and m divides n, got that backwards, n divides m. So let's suppose that a is logically equivalent to b modulus m. So then m divides a minus b, because if you remember when we were going over congruence of integers, moduluses, that was a defining property of them. So then we have a minus b equals mx, where x is an integer. So since n divides m equals ny, where y is an integer. So whence a minus b equals nyx, then we can just try to make this arrow look a little better. A minus b equals nxy. So where x, y are integers, because it's always beneficial when you have a new arrangement of variables like x times y, it's useful to define those two. So we'll just define them as an integer. So therefore n divides a minus b as desired. So by going through using the properties of congruence of integers and modulos, we were able to prove this statement, or prove this implication. So, all right, let's look at problem 4. So we have x, y, and z are integers, and x is logically equivalent to 2 modulus 9, and z is logically equivalent to 2 modulus 15. So we need to prove that x minus z divides y if and only if 3 divides y. So for this problem, it'll be beneficial if we first write out a proof strategy. So we have a biconditional here because we have if and only if. So we need to first figure out how we solve a biconditional. Biconditionals. If you remember from a truth table, that biconditionals were only true when both statements were true. So we can write x and z as 2 plus 9k and 2 plus 15j, where k and j are integers, and then find x minus z to be 9k minus 15j, which we can rewrite as 3 times 3k minus 5j, and show that 3 divides y. And then for the converse, we can show that y equals 3L for some integer L. So we can then choose L to be 3k minus 5j and work our way back to get x minus z divides y. All right. I'm trying to make a little diamond symbol here. All right, so let's begin writing our proof. So let x, y, z be an integer, and x be logically equivalent to modulus 9, and z equals 2 modulus 15. So for writing out a biconditional, it can be useful in your proof to draw an arrow, a little implication arrow, to show which direction you're starting to work out first. So we'll go from the left side to the right side. So let's suppose x minus z divides y. So then x minus z equals 2 plus 9k minus 2 plus 15j, where k and j are integers. So 9k minus 15j equals 3k minus 5j, where 3k minus 5j is an integer. So therefore 3 divides y. All right, and then we'll go from right to left now. So let's suppose 3 divides y. So then y equals 3L for some integer L. So let's let L equal 3k minus 5j, where k and j are integers. Let's actually write this as 3k minus 5j is an integer. So 3 times 3k minus 5j equals 9k minus 15j, which equals 2 plus 9k minus 2 plus 15j equals x minus z. So, therefore, x minus z divides y as desired. And we have just proved this biconditional proposition. All right, I had to make a little jump in the video, but let's take a look at problem 5. So for problem 5, we have let A be a set and B1 be a proper subset of B2, be a proper subset of B3, be a proper subset of so on and so forth up to Bn, which is a proper subset of A. So we need to prove that the complement of the indexed intersection of sets Bi union A equals the complement of the indexed union of sets Bi union A. So let's write out a proof strategy to this. And it's probably been a while since you've seen the index sets, but I thought it was good to look at them again for this problem. So we have an equivalence that we're trying to prove here. So we will show containment and reverse containment to show that both sides are equal. All right, so we can show that for the indexed intersection of sets Bi, that X is an element of B1, because we have our condition where the index sets are a proper subset of each other. As they increase. So the complement of the indexed sets Bi means that X is not an element of B1. And so, hence, we can proceed to show X is an element of the indexed union of sets Bi, or the complement of the union of sets Bi, and show containment. We can do a similar process to show reverse containment. All right. keeps wanting to make the diamond symbol and wants to twist it around for some reason. There we go. That'll work. It's not the prettiest diamond, but at least it's not sideways. All right, so let's write our proof. So let's see here. So proof, so just like doing the biconditionals, it can be useful to start by showing that we're going to show containment first. So let X be an element of the complement of the index intersection of sets BI union A. So since B1 is a proper subset of B2 is a proper subset of B3, so on and so forth. Proper subset of Bn is a proper subset of A. Then X is not an element of B1 and X is an element of A because we have union with A. So X is an element of the index union of sets, of the complement, of an index union of sets BI, and X is an element of A. So then X is an element of the complement of the indexed union of sets VI union A. So therefore, we have shown containment for the indexed intersection of sets BI union A, that it contains the indexed union of sets BI union A. All right, now let's show reverse containment. So we're going to let X be an element of the indexed union of the complement of the index union of sets BI union A. So then X is not an element of Bn and X is an element of A. Because the union of the index sets BI would be equal to Bn based on our condition that they're a proper subset of each other. So X is an element of A and X is not an element of B1. So whence X is an element of A and X is also an element of the complement of the indexed intersection of sets BI. So hence X is an element of the complement of the index intersection of sets BI union A. So, therefore, we have shown reverse containment. We have shown that the complement of the indexed union sets BI union A contains the complement of the indexed intersection of sets BI union A. And this proof is done. I realized that that was a big mouthful to say for this proof. I like that little square that it generated for me. That was a big mouthful to say for this proof, but I thought it would be great to look at index sets again for this one. So, all right, let's move on to problem 6. So problem 6, we have let A, B, and C be sets. So we need to prove that the difference of B, A, union C equals the difference of B minus A intersection difference of B minus C. So for this proof, we will do containment and reverse containment again. So start with containment. So let X be an element of B minus A union C. So then X is an element of B, and X is not an element of A union C. So X is an element of B, and X is not an element of A, and let's write it like this. X is not an element of A, and X is not an element of C. So, hence, X is an element of B minus A, and X is an element of B minus C. So whence X is an element of B minus A intersection B minus C. I'm going to write this to say or. So therefore, difference of B minus A union C contains difference of B minus A intersection difference of B minus C. All right, now let's show reverse containment. So let's let X be an element of the difference of B minus A intersection difference of B minus C. So then X is an element of B minus A or X is an element of B minus C. So X is an element of B, X is not an element of A, or X is an element of B, X is X element C. Yeah, we don't need to include B again. So hence X element of B and X is, no, we actually do have and because we can imply both. And X is not an element of A union C. So, whence X is an element of B minus A union C. So, therefore, we have shown that the difference of B minus A intersection B minus C contains the difference of B minus A union C as desired. All right, let's go to our last problem. So we have let A, B, and C be sets where B and C are subsets of A. So we need to prove that if the complement of B union C equals the complement of B intersection complement of C, then the intersection of B union C equals the difference of A and B union the difference of A and C. And if you remember De Morgan's laws, where De Morgan's laws was basically the complement of two sets can be split into the intersection or the union, whichever one operation is going under of the sets that are in the operation. So that goes back to when we were going over logical equivalence. So let's go over a proof strategy for this. So we can prove this trivially using the second open sentence complement of B union C equals difference of A minus B union A minus C. So we will show containment and reverse containment using the conditions that B and C are subsets of A. I'm not exactly the best at drawing diamonds, so. All right, so let's write our proof. So we'll start first by showing containment. So we will let X be an element of the complement of B union C. So then X is not an element of B union C. So X is an element of difference of A minus B, and X is an element of the difference of A minus C. I actually missed a part. Skipped down a line on my notes. So then we have X as an element of. So since since B and C are subsets of A, then X is an element of A, and X is not an element of B, and X is not an element of C. So X is an element of the difference of A and B, and X is an element of the difference of A minus C. So hence X is an element of the difference of A minus B union A minus C. So therefore, we have shown that the complement of B union C contains the difference of A minus B union A minus C. All right, now we'll finish this up by showing reverse containment. So let's let X be an element of the difference of A minus B union A minus C. So X is an element of A minus B, and X is an element of A minus C. Oops. Try to fix this reverse containment symbol. So hence X is an element of A, and then X is not an element of B, and X is not an element of C. So then X is not an element of B union C. So X, let's try to use some different transition words, whence X is an element of the complement of B union C. So therefore, we have shown that the difference of A minus B union A minus C contains the complement of B union C, and the statement is true trivially. So because of sideways square, there we go. So because we proved the statement being implied is true for all is true for all the conditions that are given, then we don't even need to look at the first open sentence, the complement of B and C equals complement of B intersection complement of C, because we have proved this implication trivially using containment and reverse containment. All right, so that is it for the the lectures for section 3 of mathematical proofs. Thank you guys so much for watching. Please leave a like or comment if you have any thoughts, and I will see you guys in section 4.